Let's go through leak code 1163. Last substrings in lexical order. So it gave us a string S and return the last substring of S in lexical order. So that is we want to find all of these substrings and find the lexical order, the largest one. For this question, if we use brute force, right? Brute force, that means if we use the for loop for I equals 0, I smaller than n, and j equals I plus 1, j smaller than n, right? It will be O n squared times complexity. Apparently, this is not good. So let's observe this question. So we know the first thing we want to say the last substring in lexical order. So the first thing we want to say is that we need to in order this will be largest lexical order. This substring should be extend to its end. So that first thing is that it must be a suffix, right? So this is very apparent. If we have substrings not extended to the end, any substrings extend to this end will be greater than some substring is not extend to end, right? So this is the first thing we want to say. But is that we need to extend to the end, right? And if we do brute force, what we do is that for every I from 0 to n, right? And for every j equals I plus 1 to n, right? And this will be O n squared times complexity. And what we do is that let's simulate it that way we do brute force, right? So that is if we have this string, we have I, for example here, right? And we compare the firstly we set j equals plus 1, right? And then compare character by character. So for example, if we have the SI is greater than SJ, right? We find that, for example, this is an B somewhere here. This is A somewhere here. Then that means we can move this J to the next position, right? So for example, we are already compared here, right? This is I, this J. So in this case, if we have SI greater than SJ, then all of those kind of substring which start from I plus 1 to SJ minus 1, right? Should smaller than, lexically smaller than SI, right? So the thing is that now if we iterate here, find that in now there's a special case that we find that SJ is greater than SI, right? So what do we set? For example, we have A here, we compare by A character by character, right? And B and B, and for G, we find here it is, for example, a D here, right? This is a C here, right? So now SJ is greater than SI. Do we need to brute force to move the character to SI plus 1? Actually, we don't, right? Because this is smaller than SI. All of these kind of substrings start from I plus 1 to J minus 1. We can ignore because they will not be the candidate of the last because they are smaller. So what we can do is that we can move this kind of Si to this J's position, right? We can ignore this kind of any substrings start in these positions, right? And let's we can have Si start from here, and J, for example, let it to be the next position to compare, right? So this is the second one. If Sj is already greater than Si, right? We can ignore all substrings start in I plus 1 to J minus 1, right? So this is one of the optimizations. Do we have any other optimizations? So let's thinking this simulate those kind of compare process. Okay, we have Si to I, for example, it's here, right? J is here. So we are comparing this kind of two substrings. We start with the index I and S index J. So for example, we compare for example this character, they are same. This character are same, right? So but now we have there is a B here, right? And there is a A here. So means Si is greater than Sj. In this case, intuitively, what we're thinking about is that we move this J to J plus 1 and to compare, right? Compare with Si. But we there is some optimizations here. We can move our J to this A's position. We directly any substrings start with J plus 1 to this kind of, for example, this is index, right? To this index minus 1, we should be able to ignore. Why we can ignore any substrings start from this position? Let's prove it. So we'll say this character is the same as this character, right? And this character is the same as this character. And also this character is greater than this character. So that means any substrings start from this position, right? Should have lexical order smaller than this, right? Any substrings start with this kind of position will have lexical smaller than this position, right? And we already compare Si and Sj, right? Any substrings in this range will be smaller than Si. So any substrings start in this position will also smaller than start with Si, right? So 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 that means any substrings starting in index in this range will not be the candidate. So we can have J jump to this character which has a difference directly, right? So let's um, let me copy this kind of so if SI is um, for example, SI is the the greater than SG, right? We have we can still put always we have the largest lexical as index I, right? J is the one to compare the greater one, and the thing is that we don't need to move J to J plus one. We can move J to this eighth position. Um, let's repeat this again. Why we can move is that this one has the same character as this, right? So we'll say C J plus one equals C I plus one, right? And actually S J plus one is smaller than S I plus one, right? And also we have S I plus one is smaller than SI, right? So that means the substring start with G plus one will never be will always smaller than SI. So it will not be lexical greater. So we can move this J to eighth position directly, right? So this is the first scenario, one of the optimization we can consider, right? So so in this case, we keep our I here, but we move our J to here, the first difference one, right? There are but there are some other cases when we compare an I and J, right? If now, for example, this is A, this is B, right? So Sj is greater than Si. How can we handle that? So if Sa is smaller than Si, Sj is smaller than Si. Let's just copy this. Let me. So if now this is B, right? So if Si is smaller than Sj is greater than Si. So first scenario we consider is that we 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 can move this I to J's position, right? Because every substring start in this just we discussed before, right? They are smaller, they will not be the candidate. We can have I move here, and we can have J move to J plus one, right? So in this kind of scenario. And there is another thing is that when we compare ING character by character, for example, we have this. In this kind of scenario, we'll say we can we do any more optimizations? Um, actually, of course, we can still have J equals J plus one, right? But for this kind of scenario, we can move J to here directly, right? so that we compare this character by character. So that means that, for example, this character is same, j plus 1 is the same as I plus 1, okay? J plus 2 is same as I plus 2, right? And why we can move this uh, j to this eighth position? Let's prove it. So if we for example we already these are the same, these are same, right? Um, so we'll say um because si plus 1 is smaller than si, right? Any substrings in this range we already compared. That means this kind of characters, because um, SI, they have lexical order greater than in this range, right? That means those characters, for example, CI plus 1, right, should smaller than CI. Otherwise, we'll say those kind of substrings start with CI plus 1. For example, if we have a substring with Z, for example, A, let's say SI is B, let's say D, um, D, B, A, right, C something, right? If there is a character, for example, this is F, any, that means if this is greater than this, any substrings start with F will always greater than substrings start with D, right? That means this will be lexical greater. So that means any characters in this kind of range were smaller than character CI, right? Character I. So that means any characters in this kind of range is smaller than CG, right? So we can move. So any substrings start with, for example, J plus 1, J plus 2. We can ignore it. We can move this J to this eighth position directly, right? So in this case, so this will be another optimizations, right? So that is we compare one by one. If Sj is greater than Sr, and we can move I to J and J to this kind of eighth position. This is the first scenario, right? And the second scenario is the first scenario is the Si is greater than Sj, right? Then we can move up, put our I here and put our J to this eighth directly, right? Another is our Sj is greater than Si. And when we compare, this length hasn't uh, suppress the J's index, right? So we just move this I to J and J to J plus 1. And the third scenario is that this kind of Sj is greater than Si, but but we already we compare character by character, although this is the same. And the difference, this index is greater than j, right? So we can move our I here and then move our j to this eighth position, right? So that means by doing this kind of logics, we just use 2 pointers and I and j. And I and j, those kind of pointer, they will never go backwards. Or so we break when this kind of j is going out of the range. In this case, we'll say because they are not going backwards, every index will be enumerated no more than one time. So the time complexity for this kind of approach, 2-point approach, will be On. So let's if we know these logics, the coding will be very straightforward. So let's implement the code. So let's say array plus s2 array and int n equals array dot length, and we have an I equals there, right? So j equals 1, right? So doing like this, after compare, we'll always have the greater lexical order start with I. So while say while this kind of j is smaller than n, what we are going to do is we are going to use a k variable, right, to compare one by one, and so that we move our j to j plus k plus 1, right? Or I plus k plus 1, whatever. So we'll say while this kind of j plus k is smaller than n, and array I plus k equals array j plus k, right? In this case, we keep moving the k, right? Extend those kind of case value, right? Just so we'll say if j plus k is greater equal to n, right? Well, then we can break because this kind of I to n, I to j plus k, j index j to the end is already the same as I plus k, right? Then we don't need to compare anymore, right? So we can break. So what is right is that if array I plus k is smaller than array j plus k, right? So in this case, we need to put I to j, right? So, but for our j, we can either put it to j plus 1, or if the I plus k plus 1 is already more than j's position, we put the j to this maximal value. So we'll write int t equals j. J equals max dot max j plus 1, I plus k plus 1, right? And we'll have I equals t, right? Else our I will not was because the SI is greater. We just keeping the I index, but our J can move to J plus K plus 1 directly, right? In the end, we just need to return new string array from I, right? Because I will always be greater. And if we array, we need a length, right? So that will n minus I. And let's also write a Python code as well. So let's have n equals length s, and we'll have length I j equals length s, and 0 and 1, right? So while this function j is smaller than n, what we're going to do is that let's have a k variable, and while j plus k is smaller than n, and si plus k. This is a compare factor one by one, g plus k, right? Then we're going to have k plus equal to 1, right? Um, then what we do is that if j plus k is already greater equal to n, we don't need to do any comparison anymore. We just need to break. Uh, and then if j plus k is still didn't go into the end of the s, right? Then we compare. Let's say there is a character different. So there is, if this kind of s, I just when I demonstrate, I use a C, right? I use a moment ago, S is the substring. Um, but this is the character, right? Just to make sure this is the character. If this S plus K is smaller than S J plus K, right? Then we'll still keep the ith position, right? But for our J, we so in this case, we'll put I to J's position, right? But for our J, well, we need to get a greater one, that is J plus one or I plus K plus one, right? So let's set a T a temporary variable as J, and J equals max J plus one and I plus K plus one, right? And we'll have I equals T. And let's say else. That means Si is greater, so I's position will be kept, but J will be equals J plus K plus 1, right? In the end, what we need is just return S from I to the end, right? Um, it's O(n) time complexity and O(1) space complexity.